Okay, and now that we know how we can calculate Fourier transform, we want to now take a look at some of the properties of frequency domain analysis. So a lot of these apply to the Fourier transform, but we can always get the Fourier series or make that linkage back to the Fourier series via the Fourier transform. So all of these properties actually apply to the Fourier series as well. So we know that frequency domain analysis is extremely important in analyzing signals in a variety of application areas. In fact, Fourier transforms is one of the fundamental bases behind electrical engineering. I would say it's more important in electrical engineering than it is in other engineering areas. It's also extremely important in science. So it's a really good idea to have this tool in our tool belt to be able to analyze systems and signals and things like that. So one of the types of things we want to do is, for instance, audio analysis. So here's an example of an audio signal, and there isn't too much information we can actually get from graphing it in the time domain. It just looks like a little bit of a mess. But if we graph it in the frequency domain, or find its Fourier transform, in other words, we actually get a fair bit of information from it. So we can see what the major frequency components of that signal are. And for anyone that knows music and audio, especially music, but you can associate certain frequencies with certain elements of a musical piece. So for instance, lower frequencies are what musicians will call the bass, or the bass range of frequencies. So that might represent your either stand-up or electrical bass, or notes that are really low in tone, or the big drums or things like that. Mid-range frequencies, that's typically where vocals lie, but some other instruments as well, pianos and things like that. And then the high frequencies are associated with some of the smaller instruments, and also like the snare drum and things like that. Some of you may have already played with graphic equalizers before. Usually they're either inside a musical app, or actually on the amplifier. So you can actually control how much bass or how little bass you want, or how much treble or how little treble, or how much mid-range, and etc. So one of the things we can do is we can analyze the signal, find the frequency components, and then if we want to, say, pull out the voice over the drums and the snares, then you probably want to emphasize the mid-range. And so what you do is you design an amplifier and a filter such that you provide a lot of gain to the mid-range frequencies, and you reduce the other frequencies. And that's a way of actually pulling out a voice from a recorded audio signal. We also use frequency domain analysis when we take a look at image processing. So here's an example of a filter that's moving around every pixel in this image, and it's actually taking sort of a weighted average over that and transforming the image from one to another. You'll notice it becomes blurry. Well, effectively what you're doing is actually doing a low-pass filter, and that can be implemented in the frequency domain. Frequency analysis is not just restricted to electrical engineering. Mechanical engineers actually use frequency analysis all the time to determine the health of their mechanical systems. So there's a domain called vibration analysis, which is that it's a diagnostic tool where you take a recording of the vibrations of a mechanical system, which is effectively what audio is, but you can put it straight onto the components in this case. And you get a recording, you convert it into the frequency domain, and you take a look at the frequencies and the frequencies that show up and the amplitudes of them, and you can actually figure out if there might be something wrong with your bearings or your gears or something, based on the frequencies that you should expect and the frequencies that you're actually getting. So if you have some extra harmonics showing up there, you might say, oh, we've got a jiggle in the system, we should check that out. So frequency analysis allows us to identify problems and also to design for solutions. And it can give us a lot of insight that we don't necessarily get from the time domain. Consider it, this is sort of just the big takeaway, it's just another tool in a tool belt, and it helps us to solve problems in easier ways. Okay, so one of the first properties we're going to talk about is the orthogonality of the basis functions. We all know from vector analysis of physics problems way back in the past and other things like that, that usually we want to start with basis vectors that are orthogonal to each other because it makes our life infinitely easier. It allows us to do projection in an isolated way, or decompose a vector in an isolated way. Well, we're doing the same thing when we do Fourier series and Fourier transforms. So let's take a look at the Fourier series first. So any two basis functions in the Fourier series expansion look like this, where m and n are integers. These basis functions are orthogonal in the sense of this defining integral. Sorry about that. Now note that I've had to take the complex conjugate in one case, and that's because we are dealing with complex valued functions. So the reason that we need to do that is so that, for instance, if I take the this integral with a function with itself, I have to get a positive value. In other words, I have to get the magnitude of the vector itself. Think back to inner products, and that's where it's coming from. So if that integral is 0, then those two functions are considered orthogonal. Now, I'm going to be providing proofs for all of these properties on the slides, but I'm not requiring you to be responsible for any of those proofs. You can take a big sigh now. Okay. But it's worth taking a look at these proofs if you want to get a little bit more insight. Okay, so if we take a look at this integral, put in these basis functions, we end up with this expression for the integrand, and I'm just going to use Euler's formula to split that into two integrals. So we have a cosine plus a j sine. Now note that m and n are both integers. We're always integrating over one fundamental period. If m and n are both integers, then I'm always integrating over an integer multiple of periods here. And that's why we get 0 when m does not equal n. And in fact, you get t naught when m does equal n. In other words, if I'm taking the integral with a function with itself. Okay, now what about the Fourier transform? So what are the basis functions for a Fourier transform? Well, it's really just complex exponentials at two different frequencies. These basis functions are also orthogonal. So every single frequency component in a Fourier transform is orthogonal with every other frequency component in a Fourier transform. The proof is a little bit more complicated because we have these negative infinity to infinity integrals again. But what I'm going to do is I'm just going to take a look at that expression that we get by just plugging these functions in. And I'm just going to replace omega 1 with omega naught and omega 2 with omega just to make a point. They could be anything, but I'm just going to make the point here. So then we get this expression here, but taking a look back at our Fourier transform definition, that's just the Fourier transform of an exponential at omega naught. And we already know that that is just an impulse function at omega naught. What do we know about that? Well, it is 0 everywhere except when omega equals omega naught. So as long as these two frequencies here are different, then I'm going to get 0 when I do the integration. And therefore, those basis functions are orthogonal. Okay, we're now going to look at Parsevals' theorem. So Parseval is just the man who got his name attached to this theorem. What this theorem has to do with is energy and power. So first we're going to look at power. Parsevals' theorem tells us that for a periodic signal with period t naught and with an exponential Fourier series given by the coefficients, the set of coefficients ck, then the power, which we know can be expressed in the time domain like this, can also be represented in the frequency domain like this. And let's take a look at where that comes from. So if we take a look at the left-hand side, what we're doing is we're just replacing x of t with its Fourier series, and I need to use different integers here just to so that I don't confuse the sums, and we need to do a conjugation here. When we do that conjugation, it distributes into here, and then I'm going to take out the sums from the integral. So now I have this integral. We already said that those functions are orthogonal, so that integral is 0 everywhere except when m equals k here. So that means that these sums are always 0 except when m equals k. And that's why I can actually just return to a single sum here. We have ck times ck conjugate. Well, that's just ck squared. And all that is saying is that power in the time domain is equal to power in the frequency domain. And it better be. It's the same signal. It's just two different ways of representing it. But note that's a pretty straightforward thing to calculate. So if we know the Fourier series coefficients, all we're doing is taking the sum of the squares of them. This might be actually way more complicated. We also have Parsevals' theorem for energy. So remember, when we're taking a look at non-periodic signals, we usually have to take a look at energy. And we define it like this in the time domain, and what Parsevals' theorem says that in the frequency domain, it's just the same integral with that Fourier transform instead and over frequency instead, but we have to have a 1 over 2 pi in front. And that's just a normalization constant, if you want to think of it that way. So the proof of it, we basically do the same thing we did before. I'm just expanding out what this means for possibly complex valued signals. This takes care of real signals as well. But we have to allow for x of t to be complex valued. We replace the conjugate with its Fourier transform conjugated. Inverse Fourier transform conjugated. Then I distribute that conjugation into here. Then I reverse the order of the integrals, and I reverse the order of the integration variable. And now if I take a look at what's in this square bracket, that's just the Fourier transform of x. So I replace that here, and then that just becomes capital X squared. And then notice I'm integrating over frequency. And once again, energy in the time domain must be equal to power. That should say energy. Energy in the time domain has to be equal to energy in the frequency domain. And again, it better be, because it's the same signal.